In this chapter, we are going to talk about lattice enthalpy. Now, this is quite complicated. You may need to review chapter 9 from last year before we start this, but let's get cracking and get stuck in. So let's talk about ionic lattices. Now, ionic lattices obviously are held together with ionic bonds. What we explored last year in chapter 9 was that when ionic bonds or in any kind of bonds form and atoms are brought together, like a pair of north-south poles of a magnet, they will suddenly find the attraction between them pulls them together and they clack together. We hear a sound, but actually when this happens due to the electrostatic attraction of positive and negative ions, they hit each other and we get some heat given off. It's exothermic. So what we're expecting to find is that the enthalpy change is negative. But what is it between? Well, we define it as being between the enthalpy change when 1 mole goes from gaseous ions to going into the solid lattice. And it's really clear we are really precise about from what to what, as we shall soon see. It is very important. So here is a spoiler warning. The lattice enthalpy of sodium chloride is minus 711 kilojoules per mole. The big problem is, though, is that we cannot directly measure this. This is not something that we can just measure. And it's basically because we can't get sodium chloride in one go from gaseous ions and turn into the lattice. So what we have to do is we have to find an indirect way to measure this same enthalpy change. And what we're going to do is we're going to break the process into measurable steps. Now, this breaking to measurable steps is what is known as the Born-Haber cycle, after Max Born and Fritz Haber. They took an earlier idea by Henry Hess, and Hess's law was a way of looking at indirect ways of working out enthalpies. Well, Max Born and Fritz Haber, they were the people that figured out how to do it to work out the lattice enthalpy of an ionic lattice. Let's have a look at how they did it. The easiest way to consider this is to draw the picture piece by piece to understand what all of the bits measure. So ions being higher in enthalpy than the lattice, they would have to come down in energy. Energy would be given out in the formation of the lattice. As those ions click together, then we would receive the heat coming out in the same way that we'd hear sound coming out when two magnets clicked together. This is what we cannot directly measure, so we need to construct an alternative process and look at all of the sub-processes that occur within it to try to figure out how much energy difference this corresponds to. And the first thing we're going to add is where the elements are in their standard state. You see, the elements don't exist naturally as ions. In their standard state, sodium would be solid, and chlorine gas would be a gas, neither of which would be ions. And so what we would find is that they would have significantly lower energy than the ions, but yet still more energy than the lattice. So we draw the energy level here on this diagram. From last year, you might remember that we defined the enthalpy change of formation, the delta F, to be making a particular chemical from its elements in their standard state. And so we can actually draw onto this diagram, this delta F H, as the difference in energy between the elements in their standard state and the energy of the lattice. So there we go, that black line represents the enthalpy change of formation. The next thing we need to consider is the amount of enthalpy it takes to turn both of these substances into the gaseous form. Now, yes, with this we've already got one that is a gas, but we want it as a monatomic gas rather than a diatomic molecule. And so what we've done here, this is the enthalpy of atomization, turning the solid sodium into gaseous sodium, and the diatomic chlorine molecule into monatomic chlorine gas atoms. One further thing is you can see that the arrow direction is upwards on this diagram now. That represents the fact that this is an endothermic reaction. We have to put energy in to overcome the natural attraction of these atoms to each other that makes them solid in the first place. So this section is an endothermic reaction. A little bit more energy will ionize this gas, because those electrons have an ionization energy. A small amount of energy in will remove the outermost electron. And so we call that delta IE, as in ionization energy. And this actually is something we have to put energy in, so the arrow goes up. It's an endothermic process, and this takes us to the top. So principally, we can span between the top, the enthalpy of the ions, and the bottom, the enthalpy of the lattice, by these processes on the left-hand side. They would be equivalent to the enthalpy change of the lattice enthalpy. What is on the left would be equivalent in energy to what is on the right. But it's going to get more complicated, and let's journey that way. This, generically, is known as the Born-Haber cycle. It is basically like this for any of these lattices that might form. There are subtle differences depending on exactly what is forming the lattice, and we'll give a couple of examples within this so that you're a little bit more familiar with it. So the first example is the formation of a salt crystal, sodium chloride. And so piece by piece, we want to look at what all of these steps represents when we're talking about sodium chloride. Now here we're talking about the enthalpy change of formation, and in that situation we could simply work that out by taking sodium and chlorine gas and work out how much heat is given off. Now we would do that with a calorimeter. Here is quite a sophisticated one, a bomb calorimeter. A little bit of the bomb, the ignition wires, is basically providing the activation energy which makes the sodium react in the chlorine and it forms sodium chloride. The exact amount of heat that is given off by this process would heat the water, and through Q equals mc delta theta we'd be able to work out basically exactly how many kilojoules each mole of the sodium had produced. And in this case it would be minus 411 kilojoules per mole. This exothermic process heats up the water somewhat, and we could measure it directly. And what you can see has happened is we've got the equation on the left. Solid sodium reacts with half a mole of chlorine gas and it forms NaCl. Now we want to turn our attention to the part of this diagram that we've given the letter B to. This is the atomization phase, turning it from its solid state into the gaseous form, both the sodium and the chlorine. Now the sodium is straightforward. The solid sodium will turn into gaseous sodium just with an input of 108 kilojoules per mole of energy. Now the chlorine is a little bit more complicated because we're going from half a mole of Cl2 to a single mole of Cl. Now Cl2 turning to 2 Cls has an enthalpy of atomization of 242 kilojoules per mole. Now, because we are only dealing with half a mole, we're only going to need half that amount of energy. So you can see the enthalpy of atomization, I've recorded it as 121 kilojoules, not per mole, that's per half mole. So we've killed off the mole section of that unit just to make it clearer. But now what you can see, step B in reality is going to be the sum of both of these steps. We have to put the energy in to atomize both the sodium and the chlorine. So we're going to have to add 108 to 121, and it means this step has in total an enthalpy change of plus 229 kilojoules per mole. Now we could draw these two as two separate discrete steps on our Born-Haber cycle, and in some places you will see that. So looking now at part C on this diagram, we're talking about what it takes to make those gaseous atoms turn into gaseous ions. They have to be ionized. And in this case, we want to ionize the sodium. And so what we're going to do is we're going to strip its outermost electron. And so you can see we've got the sodium gas and the chlorine gas. And then we end up with the sodium ion plus an electron that is now roaming free plus the chlorine gas. And this requires an input of 496 kilojoules per mole. And now at this stage, we need to add an additional detail. Because Cl, we know that a chlorine atom is desperate to gain an additional electron to fill its outermost shell. Those chlorine atoms, in the presence of all of those electrons floating about, there's going to be a recombination. There's going to be a situation where the electron is going to go and fill the outermost shell and make Cl, chlorine, turn into Cl minus. And this is because it has a natural affinity for gaining an additional electron. And so we call this the electron affinity. And this refers to part D on the diagram just there. And what that actually does is it actually means that before you go from ions to the lattice, there's like a sub-step where the electrons that are floating around with the ions will go and ionize the chlorine. And so it is an actual smaller enthalpy change that is now between this point at the bottom where the sodium plus and the Cl minus ions are and the actual lattice itself. So we can see that this section D has an enthalpy of minus 346. It actually gives out a little bit of energy as the chlorine combines with those electrons. It's exothermic. So putting all of those values onto this here from the left and going clockwise, minus 411 kilojoules per mole, the enthalpy change of formation. We've got the two enthalpy changes of atomization of 108 and 121, the enthalpy change of first ionization plus 496, and then the enthalpy change of electron affinity of minus 346. Now what you can see is this has enabled us to work all the way around the diagram and leave unknown just the enthalpy change of the lattice enthalpy. Now this is where we need to apply Hess's law. You see, Hess's law, if you look at the enthalpy change of formation F on this diagram, what we know is because basically this has got to go all the way up to the top and then all the way back down again, is that we know that A plus B plus C plus D plus E has got to equal F. So it's got to work its way back. And bearing in mind that F, D and E are all going to be negative, this would still work as long as we add those negative numbers. The only thing we do not know is E, which is the enthalpy change of lattice formation. So, though the understanding of everything we've done so far is quite complex, the next stage is really straightforward. We need to just plug in the numbers. And here it is. So using Hess's law, and this is where it gets complicated. We've got all of those. So A was the enthalpy change of atomization of the sodium, plus the enthalpy change of the atomization of the chlorine, plus the ionization energy enthalpy change of sodium, plus the enthalpy change of electron affinity of chlorine, plus the unknown lattice enthalpy of sodium chloride, and this has got to be equal to the enthalpy change of formation of sodium chloride. And then plugging in all the numbers, 108 plus 121 plus 496 plus minus 346 plus the unknown lattice enthalpy is equal to minus 411. And so solve that and you work out that the enthalpy change of the lattice is minus 790 kilojoules per mole. This is the enthalpy change that occurs when 1 mole of an ionic lattice is formed from its gaseous ions. This Born-Haber cycle enables us to indirectly measure enthalpy changes that we have no other access to. Now they can be more complicated than this. This is a simple example. So let's have a look at another example and then perhaps we could see how one might be different to another. Let us consider magnesium chloride. Now, magnesium chloride is going to have a different formula, MgCl₂, because magnesium is group 2, sodium was group 1. It actually creates different situations. It means that the ion that magnesium is going to form is going to be a +2 charged ion. Now that means there's going to be a change here in the top left of the diagram. Rather than just be interested in ionizing the magnesium once, we need to ionize it twice to get rid of both of the electrons. So we're going to have 2 steps over here. And then following round clockwise in this diagram, there's going to now be 2 moles of Cl- ions. And that's simply because there are 2 chlorines in every single one of these molecules. And then finally, we also have to include that on the far left-hand side to make sure we count the number of moles of the Cl twice. So let's have a look at this in a little bit more detail. These are the places where there has been changes, so we will go and focus on these areas. And here it is. Isn't it wonderful? Okay, starting bottom left, and we'll go clockwise. So at the very bottom, we have a lattice of magnesium chloride. And you can see that above that, we have magnesium in its solid state and chlorine in its gaseous state. They're the elements in its standard state. And we have that enthalpy change of formation taking us down there. Now, above that, we have the enthalpy change of atomization of the magnesium, turning it into its gaseous state. And we've got 2 times, because we're going to have 2 atoms there, the energy required to turn Cl2 into a monatomic gas to get 2Cl. So then above that, we've got the 2 ionization enthalpies to take it to the very top line, which is Mg2+, plus 2 electrons plus 2 chlorines. What's going to happen is we're going to have the electron affinity combining those electrons with the chlorines, and twice for both moles, making it into Cl-. And so we have to apply that electron affinity twice. So we have to multiply the enthalpy by 2. But you can see, even though we've added these additional steps because of the way this is different, this process is very similar to the one before. And what you could just do is remember how this is different, because you're probably in the exam going to get either like sodium chloride or magnesium chloride. These are basically the only 2 ionic lattices that you're likely to get. It's either going to be simple like the first one or more complex like this one. So it looks more scary, but what you can see is Hess's law has been modified to count the atomization enthalpy of the chlorine twice, to count the electron affinity enthalpy of the chlorine twice, and to also include the second ionization of magnesium. So with these numbers, we solve it exactly the same way as before. Here are the numbers. These will be given to you. You might even be provided with a diagram, but it's worthwhile being able to reproduce this diagram from memory so that you could understand how a different situation might vary from the one shown. So what you can see, if we put all of these numbers in, we end up here with a lattice enthalpy of minus 2,528 kilojoules per mole. The only other thing that could possibly be different to this is when we introduce oxygen. Because oxygen is an ion with a 2- charge, then we're going to get a double electron affinity step on the right-hand side. Now, unlike previously, where we were just allowing an electron to combine with a atom to form a negative ion, here we need to add 2 electrons. And what we find is that the first electron that we add is indeed exothermic, because they will snap together because of the electron affinity. With the second electron that we're trying to add, we're trying to push an electron onto an already negative ion, and that requires us to actually provide the energy, force it together. It becomes endothermic. So you can see that the first electron being added is the little black arrow, and the red arrow next to it is the enthalpy change required to add the second electron to the ion. This is significantly more complicated, but if you think of the kind of lattices that form with oxygen in, these are kind of rare situations, so you're more likely to be tested on the first 2 examples.